All right, well, we're going to continue with our look at shear stress in beams. And so our previous example, we looked at just a rectangular cross-section with a transverse load applied to it. And what we saw was that we had a parabolic distribution of our shear stress as we went down the section, and it was a maximum at the neutral axis, and it was zero shear stress at top and bottom. So we're going to go to a slightly more complicated section where we're just going to look at a T-beam. So this is an inverted T-beam, so inverted the flanges at the bottom, but the same rules apply. And so we've got our dimensions here, so it's 40 millimeters wide at the flange. Flange is 10 millimeters thick, and the web is 60 millimeters tall, and it too is also 10 millimeters thick. So, and we've been told here in the brief that the applied shear is 4 kilonewtons down, so in the negative y direction there. And what we need to do is determine what our distribution of vertical shear stress is over the height of this little beam. So when we set up really any problem, what we want to do is think about, well, what's our governing equation, which is going to help us out, and then from that equation, what are sort of what are our knowns, what are constants that we can determine, and then from there, the problem just sort of falls out from there. So for our T-beam, our governing equation our governing equation is just tau for shear stress equals VQ over IB. And that is with Q equals A1 Y1. So remember that A1 is, so for a given height that above the neutral axis, so that distance y to the neutral axis, well, A1 is the area above that section, and Y1 is the distance from the centroid of that area to our reference point at the neutral axis. And so other things that we know, and this will be a little bit of what's given in the equation, as well as just what we know from sort of shear stress in general. So we know tau max occurs at the neutral axis. And for a section where we're loaded parallel to a plane of symmetry, that's going to be the centroid of that section. So centroid is something that we should probably try to find. We also know that our shear stress varies parabolically with height y. So we've discussed that one before. So that's that's a well-known. And then well, what else do we need to find? Well, we know that we need to find the centroid. So to find just sort of constants that we need to get in order to set this equation up, well, we need we need to find our moment of inertia, so I, and y bar, and these are both going to be constants. All right. And then the other thing we need to do is find tau max. And that's going to be at the neutral axis. For our coordinate system, that's going to be where y equals 0. And then we also need to find it wherever we have sort of a section change. So what I'm going to run through is we're going to determine the shear stress distribution in really sort of two ways. The two ways are essentially the same, but they're applied a little bit differently. So one is more of a mathematical one where we will set up an equation which helps us tell the profile based upon this governing equation VQ over IB. And that's some folks find that's a good way to think about, particularly if you've already been working with a lot of math or calculus. Your brain's probably well geared up for understanding this behavior in terms of equations. So that's one way. The other way, which, like I said, is essentially the same. I don't necessarily want to call it a shortcut, but it kind of is. Essentially, what we're going to do is we're going to find our shear stress at points where we know we're going to have a change, and then we just understand that our shear stress varies parabolically over the height. Then we can just assume that plot. And so from an engineering standpoint, that's often all that we care about. We care about shear stress at a point rather than the distribution. But I'm going to show you how to do both, as there may be occasion for you to know how to do either one of them. So with that, we'll start off. And so the first thing we need to find are these constants, I and y bar, so our location of our centroid. So we'll start with our location of our centroid and find that. So y bar, just remember by definition, that's the sum of the areas times their height of the centroid to our origin over the sum of the areas. So see if I can fit you in for both of these. We'll have to go back and forth. Let's just always good to set up a coordinate point, because all of these, particularly our centroidal distance, is going to be relative to a particular location. So we'll just use point O here at the bottom corner. So we really have two areas and two y bars. So the first one is this flange, and it has a centroid right at the mid height, and then we have the web, and again centroid is right at mid height there. So let's just plug these into our equation. So we get 40 millimeters times 10 millimeters times 5 millimeters, and so that's all the flange. And then that's going to be plus 60 millimeters times 10 millimeters times 60 over 2 plus 10. And that's the web. Again, 60 millimeters times 10, that's our area. We know this distance is going to be half of 60 plus our 10 millimeters to get down to the origin. So that's our sum of our areas times our y bar of each of those areas. And then we'll just divide by the area. That's 40 times 10 plus 60 times 10. If we work all of that out, we get y bar equals 26 millimeters from the bottom of the section. Excellent. So that's our y bar is gonna be, just draw it out for reference. So y bar equals 26 millimeters right there. All right, so we have our first of our constants. We've got y bar. So that's going to be essentially our that's where y equals 0 for our as we look at our shear stress distribution. So, y bar equals y equals 0. Cool. So, and that's our neutral axis depth. That's where we're going to have, that's our location of tau max. And that's where we're going to set all of our coordinates up from there. So that's good. Now the other constant we need to find is I. As you can see, I shows up here. So let's work through that one. So what we need to do, because I is a compound, this T-beam is a compound section, we need to use the parallel axis theorem in order to compute the moment of inertia for this entire section. So, finding I. Use parallel axis theorem, and just for reference, parallel axis theorem just says that the moment of inertia of the entire section is just going to be the summation of the moment of inertia of each little piece of that section plus the area of that section times the distance of that centroid of that little section to the centroid of the entire section. So this is why we need to find y bar first, and then all we're going to do is essentially find out, well, what's our I of the web, and then we need the area of the web plus the distance of the centroid of the web to the centroid of the whole section, and then do the same for the flange, where we need the I of the flange plus the area of the flange times the distance of the centroid of the flange to the centroid of the whole section. So we'll just work that out. So we have I equals (1/12) times 10 times 60 cubed. And just for reference, that's I of the web plus 10 times 60. That's area of the web times 30 plus 10 minus 26. So the 30 plus 10 minus 26, we know the distance is, half of 60 plus 10 minus 26 is the distance to our neutral axis. So that all is squared for d squared, and that's di. And then we need to, so that's our that's for the web. Now we just need to add in the contribution from the flange, and that's 1/12 times 40 times 10 to the third plus 40 times 10 times 26 minus 5. So we have 1/12 times 40 times 10 to the cube plus 40 times 10 times 26 minus 5, 26 being the centroid distance, and 5 being the distance of the centroid of the flange, just right here. And that value is squared. So this is our I flange. That's our A flange. And this is A flange. And this is our D of the flange. All right, so that's a pretty straightforward calculation. We'll just add all of that up and work that out, and we get a moment of inertia which equals 4.77 times 10 to the 5th millimeters to the 4th. So we now have our kind of our everything we need. So we have our centroid location, we have our moment of inertia, we know what the value V is because that was given to us in the brief. So now we just need to determine the equation which describes the profile. So that's the first what we're going to do is we're going to look at it as an equation. So let me just redraw our little T-beam here. So that we can just see where we're putting the coordinate points in a little bit more detail. So that's 40 millimeters. We have our location of our centroid, and that's going to be 26 millimeters. We know this distance for our web is 10, and then our flange height 60 millimeters and 10 millimeters over the top. So what we're going to look at first is the equation which describes the shear stress in the web. So tau in the web. It's important to know too that our it's sort of how our coordinate systems are set up. So if at 26 millimeters, if at our centroid, that's going to be y equals 0. Well, in essence, what we want then is this is going to be our equation, which is going to work from the top to the bottom. So if we subtract out our 26 millimeters from our 60 and plus 10, that's going to be, this work for y equals negative 16 to 44. So negative 16 is just right down here, and 44, y equals 44 is at the top. Well, let's just start putting out our equation here, our governing equation for shear stress. So tau equals VQ over I T. So I've put T down. It's the same as B. It's just a thickness. So I apologize. Sometimes I write that out just from habit. But just keep in mind it is the same thing. All right, well, best way to do this is to start writing out what we already know. So we know the value for shear. That was given in the project brief as 4 kilonewtons pointing downwards. So because we're going to look for a stress, and I often like to work in newtons and millimeters, and that way if all the dimensions work out, everything should be in megapascals. So that's what I'm going to do. So we know there's 4,000 Newton shear force, and then we know Q by definition is A1 times Y1. We know our value of I. That's going to be 4.77 times 10 to the 5th That's millimeters to the fourth. And we know the value of T, which is in the web section, it's going to be 10 millimeters. Okay, so we still have two kind of unknowns, and I think it's always good to reinforce what we're looking at. So A1, so what we want is for some distance, and again, just to remind you, we want for some distance above the neutral axis, that distance y. A1 is the area of the section. Say for here it's above, but think about it away from the centroid. So if y goes down, it's the area below. And so, sorry, no, it is the area above. It's all the area above. So you've got A1 is the area above there. And again, if you think back to our lecture where we had our intuitive derivation of shear stress, that area. Think about we're taking deeper and deeper cuts from the top, and we're exposing the longitudinal stress, and there at the corner, the transverse stress has to equal that longitudinal stress. So that's why it's always coming down from the top. So A1 is just this area here. So we can write out what that is. So 4,000 newtons times. So A1, we know the width is 10 millimeters. And we know that the height is just going to be dependent upon the distance y from the neutral axis. So it's going to be really from the top, and then it's the distance from the top to where y is. And so if we work that out, that's 70 millimeters minus 26, this distance here. So if you think 10 plus 60, that's 70, minus 26, and then minus whatever distance is left over. So, we're looking this distance minus whatever y is. Minus y times y1 over 4.77 times 10 to the fifth times 10 millimeters. Now, what can often get people confused, we have y and y1. Remember, y is our distance along the from the centroid, and y1 is the distance from the centroid to the centroid of A1. The way we've set this up, again, it's always good to just do a kind of a sanity check, a reality check, just to make sure that the way we've organized our equation makes sense. If we have a negative value, that makes sense, because then that's a negative. So minus a negative, that's a positive. So that gives us our distance here plus whatever y is. So that's good. We seem to have that organized well. So now what we need to find is our distance y1. So y1, again, it's going to be distance from the centroid of A1 to our neutral axis. So if we write that out, and again, that's really just going to be that's just halfway between y and the top of the flange there, right? So we can just write that out as just the average, since it's just halfway. So we've got 4,000 newtons times 10 millimeters. We'll simplify this down a little bit. That's just 44 minus y. And then for y1, that's going to be 1/2 times 44 plus y. and that's all over 4.77 times 10 to the 5th times 10 millimeters. All right, well, now we have everything here. I'm going to go ahead and do just a little bit of a cleanup algebraically, just to make this a little bit easier to work with. So the 10s here cancel out. The 1/2, that 2 cancels out with the 4. So this becomes 2,000. And then we can multiply this out, 44 squared minus y squared. Again, pretty straightforward algebra. So we have 2,000 newtons, and that's all going to be times 44 squared minus y squared over 4.77 times 10 to the 5th. This is millimeters squared. This is millimeters to the 4th. So we have newtons over millimeters squared, because that squared cancels out 2 of those. And so we have tau in the web equals this equation. So that's not that's pretty good. I think that, so now that we have that, well, let's find some points of interest. So one point that we always care about is our location of maximum shear stress. So if we're working with a beam, we want to know, will it be able to sustain the shear stress which is going to be put on it? And so that's going to be, we know by definition that's going to be at our neutral axis. So that's where y equals 0. So we know that tau max equals tau sub 0, and that's going to be 2,000 newtons times 44 squared minus 0 over 4.77 times 10 to the 5th, and that gives us tau max equals 8.12 MPa. So, and again, that's the same thing as tau of 0 equals 8.12 MPa. Well, that's good. Well, let's do another sort of check. We know at the top of the section, our shear stress should be equal to 0, because there's nothing to shear against up there. You have a free surface. So at the top of the section, well, that's where y equals 44. So tau top of the web equals tau 44, and that equals 2,000 times 44 squared minus 44 squared over 4.77 times 10 to the 5th. That equals 0. We multiply through by 0, so we get tau at the top of the web equals 0. Well, that's good. That's what we would have hoped for. So that's always good when our equation works out the way that we would expect. And then now let's look at the shear stress right at the bottom of the web. So right where we have this transition. So our shear stress at the bottom of the web equals 2,000 times 44 squared minus negative 16 squared over 4.77 7 times 10 to the 5th. And if we work that out, tau bottom of the web, we end up with 7.04 MPa. So that's good. Well, now we know our distribution and some main points of our shear stress in the web. Now we need to find out, well, what our shear stress is in the flange. So we'll set up another equation. So shear in flange. And it's going to be, much the same. So we have, tau equals VQ over IT. The only thing that's really going to change is this value Q. So we have 4,000 newtons times A1 Y1 over 4.77 times 10 to the 5th times 10 millimeters times 40 millimeters. Because we now have a different width. So now what we're going to look at is an A1 in the flange. A1, and then the distance, obviously, between half the distance of this height. That's Y1. So this will be A1 flange, Y1 flange, Y1 web, A1 web. And so, again, much the same as with the web, we'll just sort of work out what our A1 and our Y1 is with respect to our centroid, and then we've got ourselves our equation. So we'll go through it just a little bit quicker this time, but it is really just the same same basic idea. So for A1, well, we know that it's a 40 millimeter wide flange, and then the distance is going to be 26 minus y times y1. And also keep in mind here that y is defined as really -16 to -26. So we always have to start with y -16 away from our centroid. 4.77 times 10 to the 5th, so that's our I, times 40, work through y1. Again, it's just going to be halfway between our distance y and the centroid, y and the bottom of the flange there. So we have 4,000 times 40 times 26 minus y times 1/2 times 26 plus y over 4.77 times 10 to the 5th over 40. Again, we can simplify 2,000, and we get tau in the flange equals 2,000 newtons times 26 squared minus y squared over 4.77 times 10 to the 5th. So there's really just one point of interest in the flange for us, and that's going to be right here where the flange meets the web. So we've already seen on just the other side, just at the web, and now we're seeing just on the underside, just where the flange is coming in. So we'll have that, tau top of flange, and that's going to be equal to 2,000 newtons times 26 squared minus 16 squared, so it's 16 millimeters down from the centroid, over 4.77 times 10 to the fifth, and that gives us tau equal to 1.76 megapascal. All right, well, now let's just, so we now have our equations for the shear stress in both the web and the flange, and we have some points of interest for us. So let's just go ahead and plot up what this shear stress distribution looks like. So I'll redraw our T-beam here. And just give us our shear stress. So we know our centroid is going to be 26 millimeters, and that's going to be our location of our maximum shear stress. So that's tau max, and if you remember, that equals 8.12 MPa. 1.2 MPa. We know at the top and the bottom, our shear stress has to equal 0. And if we come right out to our web here, in our flange, well, we know that the shear stress at the top of the flange, tau equals 1.76 MPa. We know from our equation that it varies to the square of our distance y, so it varies parabolically, so we can just kind of draw that in. And then what we also know is that at the bottom of the web, really just on the other side, some little, infinitesimally small distance on the other side where we have a change in thickness, our shear stress jumps up to 7.04 MPa. So right at that same distance, tau equals 7.04 MPa. And we also know in the web from our equation that it varies parabolically. So that's what our shear stress distribution looks like. And that's that's pretty good and pretty straightforward. But I personally think that it felt like it took a while. And there was a lot of math, a lot of algebra, and at the end of the day, really all we cared about was what the stress was at 3 points. I mean, if we wanted to plot this up and use it in a computer program, yes, we need to know the equation for the profile. But, as an engineer, often all we care about are, what's the behavior at a certain section. And so we're going to kind of run through that same process again, but, instead of going through and finding the equations for the distribution, all we're going to do is use this VQ over IT and find it at these certain points. And then we know that our shear stress varies parabolically for a vertical member. And so that's how we're going to come up with really what is the same plot. So with that said, let's just go through and run through again. And you'll see that we can do it actually quite quickly. So we know tau max is really going to be a location of our centroid. So we'll draw our little beam, and centroid of our section at 26 millimeters. Now, for tau max, that's really, y equals 0. So y is going to be right at the neutral axis, and that means that A1 is going to be the entire distance above the centroid. So that's A1, and this is Y1. So we know Q equals A1, Y1. A1 is just going to be 10 millimeters times 60 plus 10 minus 26. A1 equals 440 millimeters. Y1 is just 70 minus 26 divided by 2 equals 44 over 2. So Q equals 440 times 22. Q equals 9,680. So let's just plug that in. Tau equals VQ over IT. And keep in mind that our units here are going to be millimeters to the third, because you get millimeters squared times millimeters. So we have 4,000 newtons times 9,680 millimeters cubed over 4.77 times 10 to the 5th times 10 millimeters. Tau max equals 8.12 MPa. So we're getting the same value, and that felt a little bit quicker. Well, now let's look at shear in the flange. Tau max. So draw our T-beam again. So that's our centroid. That's our centroid there. So that's our distance, Y1. That's 26. We know that's 5 millimeters up. And we're 40 millimeters wide here. 10 millimeters wide there. So Q, A1, Y1. A1, right at the bottom of the flange. So right here, that is going to equal 10 millimeters times 40 millimeters. So A1 equals 400 millimeters. Now Y1 just equals ybar minus 5 millimeters equals 26 minus 5. Y1 equals 21 millimeters. All right, so Q equals 400 times 21. Q equals 8,400 millimeters cubed. All right, so now we have everything we need. We can just plug this into our equation. So you have tau equals VQ over IT equals 4,000 newtons times 8,400 millimeters to the cube times 4.77 times 10 to the fifth times 40 millimeters, because we're looking just in the flange there. So tau, top of flange, equals 1.76 MPa. And now if we want to look just at the bottom of the web, well, really, we can do two things. We can either, find the, A1 of the web. And so you've got some which is a positive distance and some which is a negative distance. But because we know that everything has to be in equilibrium, we can just use the A of the flange. And then the only thing which has really changed is our thickness T. And so that's my preferred way. I think it's quick. We know because they're in equilibrium, those are equivalent. So they're equivalent forces, but because the area is getting smaller, our shear stress will go up. So tau, bottom of the web, that's going to be VQ over IT equals 4,000 newtons times 8,400 times 4.77 times 10 to the fifth times 10 millimeters wide. And we find out that that equals 7.04 MPa. And essentially all we've done now is just replicated what we had in our previous example. So, we've got tau max as 8.12. At the bottom of the web, we've got 7.04. And at the top of the flange, we have 1.76. And as you can see, that's it's a lot less calculations. I find it much quicker. And then for for engineering purposes, this is often what you'll do is you just kind of, if you want to find the shear stress at a distance or at a particular point, so it's really wherever we're going to have a change. So we always want to find it at the maximum shear stress, because that's going to be a challenge for our material to come up against. So find out, can it be under that shear stress? And then you also want to, it's useful to find it at locations where you're changing dimensions. So going, for example, from a web into a flange. So I hope that was helpful. As you can see, not much different from the from the rectangular section, but hopefully now you've seen it with a little bit more of a complex material and sort of section. And with that, we'll wrap up for this example on a shear stress in a T-beam.